All right, we left off in class around here, the potential energy in a mass spring system. So there's just one more thing about this. So when a spring is stretched or compressed, so whether you're doing this or whether you're doing this and compressing it, right, it exerts a resisting force trying to get back to its equilibrium position. And since this force is capable of doing work, right, the system has potential energy. So the further the spring is stretched or the more it is compressed from equilibrium, the more force it can exert. Okay, so the more potential energy the system has. And then turning over here, there's a nice graph on page 334, which shows the kinetic and potential energy in a mass and spring system. Okay, so this graph shows us a couple things about the motion of a mass spring system that you need to remember. At the amplitude of its motion, a mass spring system has no kinetic energy and therefore zero speed, okay? And its maximum, and that's the maximum potential energy. At the equilibrium point of its motion, the mass spring system has no potential energy and its maximum kinetic energy, right? And therefore its maximum speed. And that's right here in your book. Okay. And then it walks you through equation 10.12, P equals 1/2 K delta X squared, which will lead you over here to KE of the mass spring plus PE of the mass spring is equal to 1/2 KA squared. All right, let's work through some of the on your own for 10.6. How much work is required to stretch a strong spring, K equal 3,412 newtons per meter, 34.5 centimeters. Okay, so when you work on an object, you're changing its energy, right? So in stretching a spring, you're giving it potential energy. So the amount of work done stretching the spring is equal to the potential energy given to that spring, right? So in the problem, the work required to stretch the spring will be equal to the spring's potential energy. So given K and delta X, and then you just use our formula, PE equal 1/2 K delta X squared. So PE is going to be 1/2 times 3,412 newtons per meter times 0.345 meters squared. Remember, you're going to have to take that centimeter and convert it into meters. And that's going to give PE is equivalent to 203 joules. So it takes 203 joules of work to stretch the spring 34.5 centimeters. All right, let's work on your own 10.7. A 61.2 kilogram mass is placed on a spring and set into simple harmonic motion by pulling it 23.1 centimeters from its equilibrium position. If the maximum speed of the mass is 3.4 meters per second, what is the spring constant? Okay, so by them giving us the maximum speed of the mass, it's telling us the maximum kinetic energy. So that's the first thing we're going to calculate right here. So KE equal 1/2 mv squared. So the KE max is going to be 1/2 times 612 kilograms times 3.4 meters per, my point, I do that often, 3.4 meter per second, and you have to square that, and that's going to give us 350 joules, okay? So that's the maximum amount of kinetic energy. When the kinetic energy is at its maximum, the potential energy is going to be 0, right? So then we need to use our equation 1013 and set the PE to 0. And we can use the value we just calculated for kinetic energy, and then we can relate it and get our constant, okay? So KE of the spring plus PE of the spring equal 1/2 KA squared, right? And so we're going to get 350 joules. We just calculated that, and then we just explained when that's at its maximum, this is going to be 0, right? And so that's going to be equal to 1/2 K, which is what we're trying to find, times 0.231 meters squared, and that's just 23.1 centimeters converted to meters, right? And then when you work that out, you get K is equivalent to 1.3 times 10 to the 4th newtons per meter. Okay, on your own 10.8. A 54-gram mass is placed on a spring. K is equal to 15 newtons per meter. If it is displaced 5.0 centimeters from its equilibrium position, how fast will it be traveling when it is only 2.5 centimeters away from equilibrium? This is a multi-step problem, right? So in order to find the speed, you need to find its kinetic energy, right? And then we have a way to relate kinetic energy to potential energy, K and A. And we know A because we're told how far the spring is stretched before the mass is released, right? We're given K, so we need to determine potential energy, and then we'll be all set. And we can do that, right? Because potential energy is equal to 1/2 K delta X squared. So that's the first step that we're gonna do. So the potential energy is 1/2, and then it tells us 15 newtons per meter, and they're gonna multiply that. We need to convert 2.5 centimeters into 0.025 meters, and we square that, and we get our potential energy as 0.0047 Newton meter or joules, right? Okay, and then we can take our kinetic energy of the spring plus our potential energy of the spring, and it's equivalent to 1/2 K A squared here, right? So we have our KE spring plus, we just calculated our potential energy of the spring. So we stick in 0.0047 joules right there, and that's equivalent to 1/2 times 15 Newton meters times 0.050 meters, and we square that, right? And that is just our 5.0 centimeters converted into meters. And then we get the kinetic energy of the spring is equivalent to 0.014 joules. Then we know that kinetic energy is equivalent to 1/2 mv squared, right? And we're trying to find our V, so that's perfect. So we know 0.014 joules is equal to 1/2 times 0.054 kilograms. Remember, it told us 54 grams, and we need to convert that to kilograms, times V squared. And then when we rearrange that and solve out for V, we get 0.72 meters per second. Then your book jumps into the simple pendulum. So this is another example of simple harmonic motion, and we've talked about it before, right? But we didn't look at it from the perspective of simple harmonic motion. So that's what they want you to do now. So when you take a mass and you hang it by a string or a rope and then displaced from equilibrium, it'll swing side to side in a regular manner, right? So that's the motion of a simple pendulum. And what causes this motion, you can look at figure 10.3 in your book right there, right? Right down here. In a simple pendulum, the system would rest in a way as to have the mass hanging straight down from the string, right? As illustrated by that dotted line. So I'm not going to necessarily read this to you verbatim, but just read this section in your book and understand how a simple pendulum works. And then jumping to the next page, one of the big concepts you need to know is that when the angle of displacement for a simple pendulum is small, and what they mean by small is less than about 20 degrees, the pendulum is going to exhibit simple harmonic motion. That's a big point, and you need to know it. Also, this formula right here, where you have period, and then you have length of the string on the pendulum, and then you have g, the acceleration due to gravity, okay? That's an equation you need to be familiar with. All right, let's work out on your own 10.9. What is the period of a pendulum whose length is 2.5 feet? Okay, so we're gonna take our formula right here. T equals 2 pi square root of L over G. And what you need to do is just know that they're giving it to you in feet. So I'm gonna do gravity in feet, but it doesn't matter which way you do it as long as you're consistent and you keep your units consistent. So I'm going to get 2 pi times the square root of 2.5 feet over 32 feet per second squared. And when I work that out, I get 1.8 seconds. All right, on your own 10.10, if a pendulum has a period of 0.45 seconds, what is its length? Okay, so again, we're just going to take our formula, T equal 2 pi over square root of L over G, and we know that the period is 0.45 seconds, right? And it's equivalent to 2 pi square root. We don't know the length, and then we know 9.8 meters per second squared. Then I'm going to square both sides to get this out of the square root. So I'm going to have this squared. I'm going to go ahead and square that, which is 4 pi squared times L over 9.8 meters per second squared. Multiply both sides by 9.8 meters per second squared, and I get L equals 0.45 seconds squared times 9.8 divided by 4 pi squared, and then I get 0.050 meters. You could have that in centimeters if you wanted, 5.0 centimeters, doesn't matter. Just be consistent with your units. All right, I want to go over the review questions for Module 10, so let's do that really quick. Question number 1. A mass spring system is displaced from equilibrium by 5.0 centimeters, and its period of motion is determined to be 3.0 seconds. What will the period be if it is displaced from equilibrium by 15.0 centimeters? All right, so you guys know that a mass spring system exhibits simple harmonic motion, right? And in simple harmonic motion, the period is independent of the amplitude. The amplitude doesn't affect, okay? So the period is still going to be 3.0 seconds. Question 2. What is the definition of a restoring force? A force directed towards the system's equilibrium position, which is applied as a result of the system's displacement from equilibrium. And that's just straight from the book. Okay, question 3. A mass spring system is displaced from equilibrium by 34.1 centimeters. What is the amplitude of its motion? The amplitude of the motion is going to be the maximum displacement the object reaches from equilibrium. Okay, and if you look in your book, we didn't do it, but if you read about experiment 10.2, you learn that the maximum displacement is the original distance the object was pulled from equilibrium. So in this case, it's going to be 34.1 centimeters. Number 4. What condition must be met in order for a system to exhibit simple harmonic motion? So the restoring force in the system must be linearly proportional to and opposite of the displacement from the equilibrium. And that will give simple harmonic motion. Number 5. In a mass spring system, where does the system reach its maximum speed? Okay, so because it has converted all of its energy into kinetic energy at the equilibrium position at that point, that is going to be where the system reaches its maximum speed. So at the equilibrium position. Number 6. In a mass spring system, where is the mass subjected to the greatest force? That's going to be at the amplitude. Hooke's law tells us the maximum force occurs at the maximum displacement from equilibrium. All right, number 7. In a mass spring system, where does the system reach its maximum potential energy? And that's going to be at the amplitudes. Equation 10.12 tells you that the potential energy gets bigger the farther the object is from the equilibrium. So you know in a mass spring system, the system will reach its maximum potential energy at the amplitudes. Okay, number 8. A heavy box is dropped on a spring, and the maximum compression of the spring is measured before the spring pushes the box back up. If the box is dropped from a greater height, what will happen to the maximum compression of the spring? Okay, if a box is dropped from a greater height, the spring will compress farther because the box will have more energy, allowing it to do more work in compressing the spring. Number 9, which of the following situations will result in simple harmonic motion after the mass is released? Okay, and so you have situation A and you have situation B. Situation A is going to result in simple harmonic motion because a pendulum exhibits simple harmonic motion only when the angle of displacement is small. So it's going to be A. And then number 10, last question. If a pendulum's period is measured on Earth and on the moon, where will its period be the longest? Okay, if you look at equation 10.20 in your book, it tells you that the period depends inversely on the acceleration due to gravity. Since the acceleration due to gravity is less on the moon than on Earth, the period will be larger on the moon. All right, that's it for the review questions. All right, that's it at this point. Rebecca, I haven't had a chance to ask my husband about how he would explain amplitude and displacement, so I'll try and do that and then text you guys. But I'm going to go ahead and get this video up of just the rest of the lecture and then those review problems. Let me know if you have any questions before you take your test, and good luck.